Hello everyone, I welcome you all once again to the next session of the fluid mechanics, and we are discussing fluid statics. Today we will discuss buoyancy and stability. So these were the objectives of chapter 2, that is fluid statics, and we have covered these first 5 objectives till now. And today we are focusing on the objective number 6 and 7, where we will take into consideration the concept of buoyancy and stability, and also we will have an understanding about the stability of immersed and floating bodies. First of all, the concept of buoyancy. From the day-to-day observations, we have observed that the objects tends to settle down in liquid when we put these objects in the liquid. So it is also a matter of common experience that if the object has some weight and it tends to settle down in liquid at a slower velocity than in case of the air. So it means that this liquid exerts some force on the body which tends to resist the downward motion of the object. So which means there is a force which is in the up, which is acting in the upward direction, which becomes a cause for the slow velocity or less velocity of the object when it tends to settle down in a liquid. This is in comparison to the gases wherein we can say that the force which is exerted by the gases is less in comparison to the force which is being exerted by the liquid. So this force which is exerted by the fluid, since we are talking about a fluid, it can be a gas or it can be a liquid. So this force which is exerted by the fluid on the body, and certainly it is in the upward direction, is called as the buoyant force, and this is known as the concept of buoyancy. So the most important part is that how you will try to find out the magnitude of this buoyant force. So we will again take a simple case wherein we have an object. It is a cubical object, and it is submerged. We have a liquid surface over here, and it is within the liquid surface, and this object is there, and it tends to settle down. So under equilibrium conditions, what we can say that the force which will be acting in the upward direction called as a buoyant force. What will be that force? We will try to calculate that force. So we are looking for the FB. I have given it is a subscript because it is a buoyant force. So we are trying to find out what is the buoyant force. So we will take into consideration this cubical box, and certainly we will take into consideration the pressure which is acting on the top surface and the pressure which is acting on the bottom surface. So let this the top surface of the box or the object is at a height, or it is at a depth h below the top level of the liquid surface, and x, y, z are the dimensions of this object. So z can be treated as the height of this box. So there will be a force which will be acting, that will be on the top surface, and we will call this it as a PT, the pressure at the top surface, and there will be a force which is acting in the upward direction at the bottom surface. We will denote it by PB. So let us consider, we have considered this body, and let us consider that the liquid has density rho L, and this solid box has a density rho B. Okay, so Z is the height of the body as given over here. H is the height of the liquid level to the top level of the surface. So gauge pressure, which will be acting over here by using the hydrostatic law. You can write down the gauge pressure which will be acting at the top surface, and it is certainly rho g h, and rho is basically the density of the liquid which we have taken into consideration. So if we want to convert this pressure into force, certainly it will be multiplied by area, and area of the surface is x multiplied by y. So this is the force which will be acting on the top surface. Similarly, the force which will be acting on the bottom surface will be given by same basic formula, that is P is equals to rho gh, but in that case h will be different, and h will be here over h plus z. The height will be h plus z over here. And similarly, as in the previous case, the force due to force which is acting at the lower part is called as the FB, denoted by bottom surface, is called as the bottom force, and it will be given by this formula. So the net force which is acting in the upward direction will be, you know, the difference of these two forces. So we can say that the difference between the upward force and downward force is called as the buoyant force, and it is given by this formula which we have considered in the previous case. And certainly after simplification we will get F is equals to rho L G Zxy, and Zxy can be written as V, or we can say it is the volume of the object, and we can also write it as rho L G into V, and we can write rho L into V as ml. So basically it is this volume is basically the volume of the liquid which is displaced basically, and it can then be written as F is equals to W into L. So the force that is called as the buoyant force which is acting on the body is equals to the weight of the liquid displaced by that body. So weight of the liquid that is displaced by the body. So from here, these observations we can also say that the pressure, the increase in pressure, because since we know that with the increase in the depth there is an increase in pressure, and this increase in pressure is a cause of buoyancy basically, because you know that if there will be an increase in this height, so there will be an increase in pressure, and if there is an increase in pressure, and this increase in pressure is basically is a cause of buoyancy. And from above relation, we can also say that the buoyant force is independent of the surface distance from the free surface, that is h. Also, it is independent of the density of the solid, because density of the solid has nothing to do over here. It is the density of the liquid on which the buoyant force is dependent. Secondly, the buoyant force is dependent upon the density of the fluid, as I've told you, and it is the buoyant force is basically less for gases, because the gases have less density in comparison to your solids. So it is independent of H, it is independent of rho S, but is independent, it is dependent upon rho L. Further, if we want that there should not be any kind of a moment, the line of action of these forces must be same. Let me tell you what I mean by line of action of these forces. So let me take a box over here, and it is, you know, in a liquid. So line of action of forces means these forces, the buoyant force as well as your weight of the fluid, whatever it is, weight of the box it is. So these forces must act along the same line. If they will not act along the same line, suppose one force is likewise this, another is, you know, acting likewise this, so the line of action of these forces is not same, due to which there will be generation of a moment, and certainly there will be some disturbance. So in order to have no moment, the line of action of these forces must be same, that is they should act along the same line. So based upon these observations, Archimedes' principle is there. It was a Greek mathematician who first of all, you know, observed these things, and the principle was named as Archimedes' principle, and which states that the upward force which is acting on a submerged body in the fluid of uniform density is equal to the weight of the fluid displaced by that body, and this force is called as the buoyant force. So basically this is your Archimedes principle, which states that this, which mathematically is equals to this value, that the buoyant force is equals to weight of the liquid displaced by the body for a constant density fluid, and it acts in the upward direction. What acts in the upward direction? That is a buoyant force which acts in the upward direction. So the most important thing over here is that whether the solid will remain at rest at any location, or it will submerged, or it will be floating, it certainly depends upon the difference in the densities. So if you're talking about a fluid, it can be a liquid and it can be a gas, and if both liquid as well as your solid have the same densities, so the solid body will, it will remain at rest at any location. It will neither move upward, neither come downward. So it will remain at the same location wherever it is. But if the density of the solid surface is more than the density of the fluid, so that solid body will settle down. But in comparison to the fluids, if the density of the solid is less, so in that case solid body rises to the top. So it is equally valid for both your liquids as well as your gases. The common examples in gases can be your hot air balloon. You might have observed that hot air balloon tends to rise. So basically, how it takes place. So now coming towards the stability of the submerged bodies. Submerged bodies, we have three cases over here. So the first case is a case where is the body will be bottom heavy. By bottom heavy means that the weight at the lower part will be more in comparison to the upper part, which I can say that it is not a uniform density body. The density at the lower part is more. So in case of a bottom heavy body, B will always be above G. Basically, B is the point of action of the buoyant force, and G is the point of action of your weight, or you can say it is the point where the whole weight is acting. So if B is above G, this is your case for a bottom heavy body. In that case the body will remain stable. It will not, any disturbance will tend to restore the body towards its original position, and in that case the body will remain stable. It will not topple. So any rotational disturbance will provide the restoring moment in that case. So the common example, because it's a stable case, so we will have the applications for that. Submarines, in submarines, you can say that body is also stable. Hot air balloon with the cage is also the stable one. So basically, it's a case of a stable body. So we will have the examples. But for unstable bodies, we will not have the examples. So second is the case wherein the body is top heavy, the bottom at the top portion is more, and the bottom at the lower portion is the weight at the lower portion is less. So top heavy, in case of top heavy body, the point of action of your complete weight G will be in upward direction, whereas the point of action of the buoyancy will be below this G. Certainly, it will not be here. It can be anywhere below B, below G. I have just shown it to create a difference that G will above the point of action of the buoyant force, that is B. So in that case, any disturbance will turn the body upright, and the body will topple. The third case is where we have a uniformly distributed weight. In that case, the density will be constant throughout. So in that case, B and G will coincide. B means the point of action of the buoyant force, and the point of action of the weight will coincide. It will be a case of a neutrally stable body. So in that case, the density of the body is constant, as I told you, and in that case, there is no tendency to overturn or return to its original position. If you will not disturb this body, it will remain as it is, and if you will disturb it, it will remain as it is after the disturbance. So it will not tend to regain its original shape. This stable body after disturbance tends to regain its original shape. In this case, and the body topples. That is the case of your unstable body. It topples. And in case of a neutrally stable body, it doesn't come to its original shape. It remains where you will where you want to keep it. So this is a case for neutrally stable body. So let me tell you, you have to remember that these cases are for the submerged bodies. These all bodies will be submerged in your liquid, or it can be your gas. So submerged cases will be there. So these are the three cases. So next, we will take into consideration the cases of the floating bodies. Very important. So in that case, I have taken another, again a body wherein I have shown the liquid surface because it's a case of floating body. So if the body is bottom heavy, in this case, bottom heavy means B is above G, means weight over here is more in comparison to the above. So in that case, the body again will remain stable as it was the previous case. Any rotational disturbance will produce the restoring moment. So this case is similar to the case of your submerged bodies. But in the second case, if the body is top heavy, that is G is above B. So you can see over here we have put 2 points. G is above B. The body may or may not be stable. In the previous case, the body was not stable. If G was above B, the body was not stable. The body, will topple in the previous case, that is in the case of a submerged bodies. But here, the body may or may not be stable, which means we have to look into the conditions where the body will be stable and where the body will not be stable. So let me tell you what will happen if there will be some disturbance. On small disturbance, what will happen. This is a small disturbance which is shown over this point. B will move towards this point, because this point of force of buoyancy or buoyancy force will act in the upward direction, in the vertical direction. So this point will shift, this B will shift from B to B dash. Okay. So, but the G will remain unchanged. It will not, this point will not, uh, this will not, change its position. It will remain same. So the stability in this case is, in this case where we have the top heavy case for the floating bodies, the stability is governed by means of metacentric height, and we denote that metacentric height by Gm. So G, it is the point where the whole weight is acting, and M is basically the point of intersection of the line of action before and after the disturbance. Suppose the line of action before the disturbance was this, that, and line of action after the disturbance is this. So point of intersection of these two lines will be your called as a point M, and we call it as a meta center. We call it as a meta center. So now this meta center basically will decide whether the body or whether the floating ship will be stable or it will not be stable. The point of the location of this point will decide. So now what we have if Gm is positive, which means Gm is positive. Positive means that M is in the upward direction. If M lies above G, then we can say Gm is positive. And if M lies below G, then we can say that Gm is negative. So if M lies above G, what will happen? So why we're talking about is there will be some disturbance, and on the disturbance, whether the body will tend to regain its original shape or not. If it will tend to gain its original shape, then original position, then it certainly means that the body is stable. And if on the small disturbance it is not coming back to its original position, so it certainly means that the body is unstable. So if Gm is positive, so on small disturbance, what will happen? A restoring couple will act and the body will return to its original position. How restoring couple will act? See, this is the case after disturbance, and you can see this is your, just wait. Here you can see we have this force which is acting over here, and we have this buoyant force. So if you will see after disturbance, we have this kind of two parallel forces which are acting over here, one by weight and one by due to your buoyant force. So what will happen? it tend to this, it will form a couple because it is at certain distance. So what will happen, it will tend to form a couple which will be in anti-clockwise direction. And anti-clockwise direction, because you can see, if you extend like this, it is in this direction. So if this anti-clockwise direction couple which will be created over here, it will try to bring the body towards its original position. And since it is trying to restore the original position, we call it as a RC, or we can call it as a restoring couple, which we're talking about over here. This is certainly due to these forces which are acting over here. So if GM is positive, M lies above G, any small disturbance will become a cause of restoring couple, which will try to bring the body towards its original shape, and the body will be stable in this case. Secondly, if GM is negative, which means this M will be below G. There can be a case where M will be below G. So this is the second case where M is below G, that is GM is negative. So any small disturbance, instead of restoring couple, an overturning couple will act, and the body will not return to its original position. Instead, it will topple. What will happen? See, we will have the buoyant force which is acting like this, and we have the force due to the weight, or due to uh, the weight of your body. So you can see, if you will see this, the couple produced by these forces, which it will be in this direction, that is, it is in clockwise direction. So since the body has disturbed towards this direction, and the couple is also acting in this, in the clockwise direction, so on small disturbance a further disturbance will come due to this couple, and what will happen, the body will overturn, and we call this couple as a overturning couple, which will not bring the body towards its original position, rather it will overturn the body, and we will call it as overturning couple. So the body will be unstable in this case, in a case where GM will be negative. So in case of floating bodies, we have two cases. One is when B is above G, the body will remain stable. There is another case when G is above B. In that case, the body may or may not be stable. The body will be stable only and only if M lies above G, which means GM is positive, metacentric height is positive, and the body will be unstable when M lies below G, that is GM is negative. So this is a case of a stability for floating bodies. Now coming towards the last part of this chapter, that is metacentric height. It is very important again. So since we are talking about the floating bodies, and for stable floating bodies, you know that the metacentric height must be positive. It is very important, which we have studied in the previous slide. So it is now important to understand the functional relationship between the geometry of the body and the metacentric height. And again, we have that kind of a body which will be a floating one, and you can assume that it is a case of a floating body, and simply it is a case of a ship. So the metacentric height can be, I have not given the derivation, complete derivation. The metacentric height over here can be given by this formula: GM is equals to BM minus BG, and BM is basically, it can be calculated by using the derivation, and it will be equals to I by V, where I is the moment of inertia of the plane of flotation about the centroidal axis, and V is the immersed volume. Immersed volume means the volume of the body which is in the liquid, and Bg is the distance between the center of gravity and the point of action of the buoyant force. So you can appreciate these points B, G, and M. So Gm is equals to I by V minus Bg. So in order to find out the metacentric height, you have to use simply this formula, although there is a derivation, complete derivation uh, for finding out this metacentric height, which we are not discussing in this video. So you can find out this GM by using this formula. So talking about I, what is this? We have the I, for the center about the centroidal axis, and it will be different for different axes with respect to different axes. So suppose we have the top view of this uh, object or this body. This you can assume as the top view. So you can see that this is the x-axis which I have shown over here, and this is the y-axis, and the axis which will be in the perpendicular direction, which is acting normal to the surface of your phone or your laptop. That axis is the z-axis, which you can see over here. So this is basically the top view of this surface. So you can assume that if it is a case of a ship, you can assume that this shape will certainly be likewise. The shape will certainly be likewise this. So you can have this kind of a shape for the ship. So in top view, if you will see the ship, it will be likewise this. So we will have two axes. One is the rolling axis. You can see this, and we will have the another axis that is along the x-axis, which is called as the pitching. So basically when a ship floats, so we have the rolling axis, we have the pitching axis, and we have the spinning axis also. But as far as the rolling axis is concerned, if there is a movement of the ship with respect to y-axis, we call it as a rolling, and if there is a movement of the ship with respect to upward and downward movement of the ship with respect to x-axis, we call it as a pitching. So when we are talking about stability, and we are talking about stability with respect to rolling, which means we are talking about stability with respect to y-axis. Rolling means it is around the y-axis. So in that case, the moment of inertia about the y-axis should be considered. So we will take into consideration the moment of inertia I y if you are talking about the stability in the y-axis or with respect to rolling. So, but if you're taking into consideration the stability with respect to pitching, that is with respect to your x-axis, so the moment of inertia will be taken about the y axis. So it is up to you. You have to find out the stability in both the cases. That is with respect to x-axis, with respect to y-axis, that is with respect to pitching and with respect to rolling. So you have to put the appropriate values of your moment of inertia in order to find out the metacentric height. Okay, so this metacentric height which we discussed is the application of buoyancy and stability. So this is an application of what we discussed in the previous slides. So this was all about the buoyancy and flotation, and as an application part, your metacentric height. So with this the theoretical part of your chapter fluid statics is over, and in the coming videos we will talk about the numerical portion of this subject, that is your fluid statics. So these were the books which were considered or referred during the course of action. So I thank you very much for watching this video, and we'll join back with the numericals in the next videos. Thank you.